Hello students, I will continue with the probability of error derivation for ASK. So already we have looked at the definition of ASK. It's representation in time domain. We have looked at the signal space diagram of ASK and we just started with the error probability derivation for ASK. Now let the transmitted modulated signal be represented by S of t as mentioned earlier. S of t transmitted signal is affected by additive white Gaussian noise W of t, which is of zero mean, which is assumed to be of zero mean, and variance is n0 by 2 because it is a white noise and the white noise power spectral density is constant throughout the frequency range. So the received signal is represented by X of t, which is a summation of transmitted signal S of t plus the noise component, that is W of t. When we look at the covariant detector diagram, so this is my covariant detector. So the signal which is fed is the received signal X of t. It first gets multiplied with the carrier basis orthonormal basis function phi 1 of t. As I have already told that ASK is a one-dimensional modulation technique, so there is only one carrier signal, that is phi 1 of t. So X of t and phi of t are multiplied and then integrated over a single bit duration PD. This multiplier followed by integrator is called a correlator, and the output of correlator is x1, which is compared with the threshold. Threshold is denoted by lambda here, and the value of x1 is greater than threshold. The decision is taken in favor of binary 1 transmission, and x1 is less than lambda, the decision is taken in favor of binary 0 transmission. So that takes place in the decision device. So let us now first find out what is x1. As we can clearly see from the diagram, x1 is integration 0 to tb x of t multiplied by phi 1 of t. That is the output of integrator. And x of t, we have assumed, let's say I am transmitting symbol 0. So this is my equation of x of t. X of t is equal to S of t plus W of t. In case of ASK, S of t is 0 because when input is 0, we are not transmitting any signal in a amplitude shift key modulation technique. So S of t value is equal to 0. So we can say that X of t is only equal to W of t. So we have made the substitution over here. Instead of X of t, we did W of t multiplied by phi 1 of t dt, integration over a single bit duration. That gives us x1 is equal to W1. Now, which indicates that the output of code x1 is only equal to the noise component W1. So if I want to find out what is the expected value of this variable x1, that's equal to the expected value of W1, or expected value is also known as the mean, and mean of W1, I already told AWGN is of 0 mean, we have assumed. So mean of W1 or mean of AWGN is equal to 0. And the variance of x1 is equal to the variance of W1, that's equal to N0 by 2. Because the signal over here, received signal is only equal to the noise component, as in case of ASK, when we transmit 0, there is no waveform present in the output. So only we are receiving the noise component at the receiver. Now we will compute the probability of error of first kind. So probability of error, what exactly is probability of error? So I have assumed that I am transmitting binary 0. Now if at the output of decision device I am able to detect 0, I am able to take a decision that 0 was being transmitted, then absolutely there is no error. But if a 0 is transmitted at the transmitter, but I take a decision in favor of binary 1, then there is an error occurring. Because 0 is being transmitted, but what I have concluded decision at the receiver is I am saying that 0 was transmitted, which is a wrong decision. So the probability of error is the probability of making an error. Under what condition we can make error, we will see. Now just a recap of the signal space diagram from ASK. Already we have seen this. Phi 1 is a single carrier, two symbol points, binary 0, binary 1. Magnitude of binary 0 is 0, magnitude of binary 1 is root over of EB. Now if I want to divide this decision space into these regions, where should I draw the boundary? Exactly at the midway of the two signal points. So this point magnitude is 0, this point magnitude is root over of EB, So if I draw a boundary exactly at the midway, the value of the boundary is root over of EV divided by 2. And the region to the left of the boundary, I am calling it as region Z2, and to the left of the boundary I am calling it as region Z1. Now assume that we have assumed that binary 0 was transmitted. Okay. When binary 0 was transmitted, it gets affected with noise, and let's say the noise component is so much that the received signal lies in region Z1. If the received signal point lies in region Z1, which is the closest message point in region Z1, that is your message point 1, binary 1. So decision will be taken in favor of binary 1. But if the noise interference is less, then if the received signal point lies in region Z2, it is close to symbol 0, and decision will be taken in favor of symbol 0, which is a correct decision. But if 0 is transmitted and the received signal or symbol point lies in region Z1, decision will be taken in favor of bit 1, which is a wrong decision. So probability of error is, if you are transmitting 0 and the received signal lies in region Z1, a decision at the receiver is taken in favor of binary 1, then it is a wrong decision. And let us compute the expression, what is the probability of making an error in an ASK technique. Okay, so my decision boundary, so I will make an error if I am transmitting 0 and the received signal lies in region Z1, there is an error. And if you look at decision region Z1, it extends from this value, this point is root over of EV by 2, and this side it extends up to infinity. So I can say that if the received signal point, that is the output of the correlator, is between root over of EV by 2 to infinity, then there is a chance of making an error. Okay. So the decision region of making an error is if the value of x1 lies between root over of EV to infinity, that is your region Z1. Since x1 has a Gaussian distribution, it is defined by, we know the Gaussian distribution PDF. So this is the PDF of the Gaussian distribution. The random variable is capital X, small x1 is the dummy variable. Conditional, we call it as conditional probability. This is condition that what was being transmitted, we have assumed that 0 was being transmitted. We can also do it in the reverse way. I can also assume that symbol 1 is transmitted, and in that case the decision region or the probability of making an error will happen if the received signal point lies in region Z2 and decision is taken in favor of 0, then in that case the decision region will extend from minus infinity to root over of EV by 2. We can do it either way. So we will move on with the assumptions we have done in the beginning, that is the symbol, let's say the symbol 0 is being transmitted. Okay, so condition probability f x1 of x1 is the random variable and small x1 is a dummy variable of this random variable. Condition that what was being transmitted, condition that 0 is being transmitted is equal to, now this expression is the generalized expression for probability density function of a Gaussian distribution. 1 divided by root over of 2 pi sigma square. Sigma square is the variance of this random variable capital X1, e to the power minus of x1 minus mu whole square divided by 2 sigma square. Mu is the mean of the random variable capital X1 and sigma square is the variance of the the random variable capital X1. Okay. So conditional probability when 0 is being transmitted, I can just, this is a generalized expression, let me put the values of variance and mean we have derived earlier. We got mean equal to what? We got mean E of x1 is equal to mean of E of x1 or the mean of x1 is 0 and the variance of x1 is n0 by 2. So I substitute these two values in this expression of conditional probability. So in place of mu 0 is put and in place of variance sigma square substituted n0 divided by 2. Similarly here also in place of sigma square n0 divided by 2, 2 gets cancelled, here also 2 gets cancelled. So the remaining expression over here is 1 divided by root over of pi into n0 e to the power minus x1 square divided by n0. Okay. So this is my conditional probability or PDF. What is the relationship between probability and PDF? You can get the probability by integrating the PDF. So we have the PDF expression. If I want to find out what is the probability of symbol error when symbol 0 is being transmitted, so I will call it as PE of 0. Probability of symbol error when 0 is being transmitted is equal to, we have to integrate the conditional probability. Integration of PDF is equal to the probability. So integration of PDF expression, the conditional probability expression I have written here, and in further step I will substitute equation number 5 in place of x1 slash 0, and look at the limits of integration. Root over f. What is the probability of making an error? The probability of making an error when 0 is being transmitted is the probability that the received signal lies in which region? Z1, and Z1 region extends from root over of EB by 2 to phi 1. So the limit extends from root over of EB by 2 to infinity. Fx1 x1 slash 0 dx1. Just substitute equation number 5 and 6. Substitute this conditional probability, whatever we have reduced over here in place of this substituted, and then let us make few more simplifications in order to arrive at the final expression. So P of 0 is equal to, limit remains the same, integration 1 divided by root over of pi into n naught, root over of pi into n naught, e to the power. I can just rearrange this and write like this. If you look at this expression, 1 divided by root over of pi naught e to the power x1 square. So this x1 square divided by n naught can be written as x1 divided by root n naught whole square. So that's what is done here. So e to the power minus of x1 divided by root n naught whole square dx1. Let us say this component x1 divided by root over of n naught is equal to z, or which implies x1 is equal to z into root over of n naught. And if I take the differential quantity, so dx1 will be equal to dz into root over of n naught. We can replace the limits of integration as well. So when x1 is equal to root over of eb by 2, your z value is 1 by 2 root over of eb by n naught. So x1, when the value of x1 is root of eb by 2, value of z is 1 by 2 root over of eb by n naught, and when x1 is equal to infinity, at the same time z is also equal to infinity. So replacing the variable from x to z, so magnitude is as it is, 1 by root over of pi into n naught. In place of dx we have written, in place of dx we got dz into root of n naught, that's substituted here, and this entire quantity was assumed as, this x1 divided by root n naught was assumed as z, so that is put as it is, z square. So the probability of error P of 0 is integration, limits is changed, and finally we are getting integration 1 by 2 root of ab by n naught to infinity, 1 divided by root 2, root n naught, root n gets cancelled, e to the power minus z square dz. Now this probability of error expression what we got, we are going to use the definition of the complementary error function here. So what is the definition of a complementary error function? Complementary error function defines that ERFC, complementary error function of u, is defined as root over of m2 divided by root over of pi integration u to infinity e to the power minus u square du. So I can just rearrange this equation number 8 in such a way that we can use the definition of complementary error function and rewrite expression number 8. So rearranging, we can say P of 1 by root over of pi into 2 divided by 2, and we can rearrange it. So 2 by root pi into this quantity can be represented as error function, complementary error function of u. U is the lower limit of the integration. So here the lower limit of the integration is 1 by 2 root over of eb by n naught. So I can say, so 2 by root pi entire quantity. So remaining is 1 by 2. So 1 by 2 is here. And this 2 by root pi, this entire thing, by using the definition of error function, I can say it is complementary error function ERFC of u. U is the lower limit of the integration. So 1 by 2 ERFC of the lower limit of the integration is 1 by 2 root over of eb by n naught. Okay, so this is the property of making an error when symbol 0 is being transmitted. Similarly, I can also find out the probability of error when symbol 1 was being transmitted, and it is exactly the same expression as expression number 10. So 1 by 2 ERFC of 1 by 2 root of eb by n naught. Now the probability of sending 0 or 1 is equal, that's equal to probability of 0. Sending 0 is equal to 1 by 2 and probability of sending 1 is also equal to 1 by 2. So the average probability of error expression is PE, which is equal to P of 0. Probability of sending 0 multiplied by probability of making an error when 0 was being transmitted plus probability of sending 1 multiplied by probability of making an error when 1 was being transmitted. So we're going to substitute P of 0 is 1 by 2 multiplied by this, which obtained earlier in the previous step, plus 1 by 2, so 2 times. So finally the expression of the probability of error for ASK is PE is equal to 1 by 2 ERFC of 1 by 2 root over of EP by N naught. So this is the final probability of error expression for amplitude shift keying technique. Thank you.